Hello students, today we'll start a very interesting chapter, that is work and energy, right? And in lecture 1, I will describe first the concept regarding work, power and energy. And these three words, they are correlated to each other. So that's why first we are starting with work, then we will move to power and energy. Okay. So let's move. Now work. All work you are doing, and sometimes your guardians are telling that you are not doing anything and you are sitting on the chair, right? So that means the work done on an object is defined as the product of magnitude of the force acting on the body and displacement in the direction of the force, that is work done. That means I am just giving you here this lady, you just see, she is pulling some box. Now, if I am doing some work, I am writing here, if I am doing some work at that time, work done, this W I am representing, that is the work done, and F, that is the force, S, that is the displacement, okay, or the movement of any object, right? Now that means work done, you have done one work, that means you have applied force and there is some displacement of the object. Suppose you are carrying one box, that means what? You are carrying one box and you are moving somewhere, so that means there is some displacement here. So the work done, that is the product of the work done, that is the product of F and S. That is the force you are applying and displacement you have. At that time only I can say that you have done the work. Suppose S equals to 0 and you are applying a lot of force. At that time, what will be work done? That is the F into 0. That means 0. That means 0 work done you have. So at that time, we are not calling this is the work done, or at all we will not say this is work. So work done, that means there should be some displacement in the direction of the force. Suppose you have one object here, and if you are applying the force in this direction, so this object should move in this direction. If it will move in this direction, at that time I will say that yes, you are a very good boy or good girl and you have done the job or you have done the work, right? So this W equals to F dot S, F into S. Please remember this thing. Please remember this equation. This is very, very important, very important equation. So please remember this thing. So now I think you have a clear idea regarding the work. Work done, that means there should be some displacement. No displacement, no work. Yes displacement, yes work, right? So work done on an object is defined as the product of the magnitude of the force acting on the body and the displacement in the direction of the force. Now, what is the unit? I have done the work, ma'am. So what will be the unit? How I can tell you, yes, ma'am, I have done this much work, that much work. So the SI unit, that is the Newton. That means now you are able to tell me, yes, I have done 1 Newton work, ma'am. I have done 2 Newton work, ma'am, right? So this is the SI unit of the force is what? Newton. And the great scientist Newton, according to his name, it's the Newton. So if the force acting on a body causes no displacement, work done is 0, and why 0? Already I have described. So if you are pulling any object or you are pushing any object, the direction of the displacement should be there, and there should be some value of the displacement. Until unless I will not tell you, yes, you have done some work, right? Okay, is it clear? Now, next. Always it is not able, suppose I am applying, this is a box and I am applying the force in this direction, okay, and with the horizontal, this is horizontal, assume that, because my drawing is so good, so please assume that this is horizontal. Now with horizontal line or x-axis, this force will make the angle theta. It will make the angle theta, okay, it will make the angle theta, right? Now this component is the f cos theta, this component is the f cos theta, and the force component f cos theta gives the component of force along the direction that body is displaced. So what I am doing, I am pulling in this direction, but the body is moving towards the force direction, but with an angle theta, right? This is the ground over which, or this is the surface. This is the surface over which I am just pulling this one. So at that time, you can see that the object will move in this direction, and this angle is your theta. This angle is your theta. So the component that, or displacement, that is the f cos theta, and cos theta is the angle between the force vector and the displacement vector. Here, this is the force vector, and where it has been displaced, this one. So this is f cos theta. So this one is the theta. That means f cos theta. So that will be the displacement vector. So cos theta is the angle between the force vector and the displacement vector. Is it clear? So if I am pulling the object, always it is not like that. It should go straight forward. It may be I am pulling the object with an angle. I am pulling the object with an angle, right? It is not like that I am sitting on the ground, then I am pulling it. You are doing this thing. No, you are just fastening one wear or anything. At that time, you are just pulling it because your height is higher. At that time, you are pulling it with an angle theta. With an angle theta. And if you are very, very tall at that time, this theta is very high amount, right? This theta is 30 degree for me. If you are your height is very good, then theta may be 60 degree. If a very long person, then theta may be 120 degree. So that because I am just grabbing this wear here, right? So at that time, you can see that the theta is the angle between what? Between the force vector and the displacement vector. Clear? Fine. Now, a very good definition, like a very good boy or good girl, that the scientific definition of work is a little bit different. The definition of work in physics that has the relationship to energy. Whenever work is done, energy transferred. So I have told you there is a correlation between energy and work. The physicists, they are also doing the same thing, right? So for work to be done in a scientific sense, a force must be exerted and there must be some displacement in the direction of the force, in the direction of the force, right? So this is the definition of the work. Now, work is the product of component of force and the force in the direction of the displacement and magnitude of this displacement. So mathematically, F equals to force. So F into S, that is the W. Now, whenever F cos theta, this is the displacement vector, then this into S, or I can tell if S equivalent to D distance, so I can tell this into D. Okay, so this much has been written here. If there is an angle of pulling the force, so F cos theta into D or F into D. So where W is the work, F is the force, theta is the angle between what? Theta is the angle between the force and the displacement vector theta is the angle between these two. So F cos theta into D, and D is the distance, how much it will travel. So this is the work done, right? Now the dimension of the work, that is the whatever your m L square T to the power minus 2. Now unit of work. Unit of work, the SI unit of work, that is the joule, which is defined as the work done by a force of 1 Newton in moving an object through a distance of 1 meter in the direction of the force. So joule is the unit. Now joule means what? 1 joule equals to what? I have to apply 1 Newton force. I have to apply 1 Newton force. What will be the displacement? 1 meter. 1 meter displacement. Then I will tell that 1 joule work has been done. 1 joule work has been done. Right? So now you can define, if someone is asking you what do you mean by joule, 1 joule, then you have to define in this way. If I am applying force of 1 Newton in moving an object through a distance of 1 meter in the direction of the force, then the work done equal to 1 joule. Okay. Now see, this is a person who are lifting 25 kg. Wow, what a weight. Fine. Now 2 meter is the distance from the ground. Okay, 2 meter is the distance from the ground. So work done equals to how much? This is an example. We'll do a lot of numericals related to this one, because from this in your different competitive examination, they will give you different mathematical problems or numericals. So we'll solve in such a way that you will be able to find out the solution easily, right? So, okay, now come to this one. Work done, that is the mass into acceleration due to gravity. What that is, force equals to m into a, where m is the mass and a is the acceleration. If you are lifting something, then this acceleration is the acceleration due to gravity, right? If you are lifting something. So this is the acceleration due to gravity. That means at that time, F equals to m into g. And work equals to, you know that F into the distance d or displacement, or m into g into d. So now you can find out what is the mass. The mass is 25 kg. What is the g? 9.8 meter per second square. And what is the d? 2 meter. So at that time you can find out what will be the work done, right? Here we have used what? F into D or M into A into D, or you can write down M into G into D, because here A acceleration is the G. Okay, G. Okay, G. Now, factors affecting the work. Factors affecting the work. Force is defined as the push or pull. Fine. And it will change the velocity and acceleration because mass is constant. Now, the work that is equals to force into the distance. Now, how much distance it will move, that depends on the acceleration, right? Yes or no? And force is the MA. Force is the MA, where M is the mass. If I write here, mass into acceleration into distance, right? So the mass is constant. We are thinking that thing, mass is constant. So it depends on the acceleration, it depends on the distance. And distance also depends on the how much force you are applying. So force is a vector quantity, has magnitude and direction all. If the force acting on an object is zero, irrespective of the state of the object, the work done by the force is 0. So here you can see that it will depend, the work done depend on acceleration as well as the distance, right? And also force, the applied quantity of the force. And it is very, very important in which direction you are applying the force and in which direction the object is moving. That is also very, very important. So please remember all these points and try to understand what I am just going to tell. Now the displacement. Displacement is a vector quantity that gives the shortest distance between two initial position and final position. Suppose this is A point and this is B point. This much is called displacement. But I can move from point A to B following this path. I can move following this path. So I can move following so many paths, right? But this is the shortest distance, and this AB vector, this is called the displacement. This is called the displacement. If I push a rigid wall with all our, or whatever the force I can do, I will just push it, but still it is not moving. So that means I am not doing any work. No work has been done. If the resulting displacement in the direction of the force due to the force acting on the object is 0, if the resulting displacement is 0, at that time, because at that time work done equals to 0, because work done, that is the force into displacement, right? Force into displacement. Suppose I am giving one, suppose this is a circular path from A, you are just moving in this circular path and you are coming to this point. What is the displacement? The displacement is 0, because displacement means from initial and final position there should be some value, magnitude as well as direction. Here direction and magnitude, if you consider this vector, then if the displacement is 0 for the circular path, right? So that means at that time work done equals to 0, right? That thing has been written here. First, I have told you that displacement, this is a vector. This is a vector quantity that gives the shortest distance between the initial position and final position. Then I have told you, if displacement vector equals to 0, work done equals to a big 0. And if I push a wall, the wall will not move, because I don't have so much force that it will break down and it will move. So that is possible in movie. It is not possible here. So work done at that time is also 0. Okay. Here the picture shows the displacement that I have drawn there. Suppose this is point A and this is point B. So the displacement vector, that is AB vector. Displacement vector, that is AB vector. And the distance may be somewhere. If you are moving this, okay, that is the AB vector. That means the shortest distance between you and your school, that is with the displacement vector. But if you are roaming here and there, here and there, here and there after your after school time, and then you are reaching at your home, I will not tell you you have followed the displacement vector. I will tell you that you have crossed some distance, not the displacement vector. Okay, got the point? Now, the work done by force on an object can be positive, can be negative, can be 0. It depends on what? It depends on the direction of displacement. Suppose this is an object, I'm applying the force here, but it is moving in this direction. I am just throwing one object, at that time it is coming to my hand. Suppose I am just throwing one object upward, after some time it will come to my hand. Several displacement vectors may be there. That means the direction of the displacement vector may be positive, may be negative, may be 0, right? I have something and it will just cover this circular path. That means displacement vector is 0. So the work done is 0, right? So this has been written here. For any object moving in the opposite direction to the direction of force, such as friction acting on an object moving in the forward direction, the work is done due to the force of friction is negative, right? So here also the force of friction is very, very important. I am applying some force, but the force of friction, as you know that if this is an object, I am applying the force in this direction. The frictional force will be in opposite direction. The frictional force will be in opposite direction. Suppose your F that is less than your frictional force, right? Frictional force. And at that time, you can see sometimes what happens if you have a slanting path and one box is here, you are pushing something, but it is sliding down. At that time also, the direction of this displacement of this object is in opposite direction. At that time, it may be negative. Okay. Next. Now, the object experiences a zero force when the angle of displacement is perpendicular. What I have told, this is force and this is the horizontal, assume. Okay, as usual, I have drawn horizontal line like this, and theta is the angle. Now, if theta that equals to 90 degree, that means this type. Okay, this is force and this is F cos theta, cos 90 degree. At that time, you can see that F cos 90 degree, at that time you can see that you have zero force. Zero force when the angle of displacement is perpendicular to the direction of the force. So a coolie lifting a mass on his head moving at an angle 90 degree with respect to the force of gravity. At that time, work done by the gravity on this object is 0. Because cos 90, that is 0. So that means F cos 90 degree equals to 0 and work done equals to nothing but F cos 90 degree into displacement. Whatever the displacement, I will not bother this one because this becomes 0. So it is a big 0, right? Work done is a big 0. Clear? So if the object experiences a zero force when the angle of displacement is perpendicular to the direction of the force, at that time work done becomes 0. Now the energy. Okay, with a lot of energy, I have told all those things. Now I will define what is exactly the energy. Energy means the ability to work. If you have less energy, you have less capability to work, right? Less energy, less capability to work. That means it is the ability to do work, and its unit is same as the work. Energy is scalar quantity. There is no direction here. Energy is scalar quantity, and SI unit of the work, SI unit of energy or work, that is joule. That is joule. Okay. Next, the forms of the energy here, it may be kinetic energy, it may be potential energy. And potential energy we are writing in terms of our P dot E. And kinetic energy, we are writing K dot E. We are writing K dot E. Okay. So kinetic energy and potential energy. Next, what is kinetic energy? Before going to explain this kinetic energy, I like to do one thing, that I like to do one activity. Suppose you have a sand here. This is a picture of desert. So please don't go to desert to experiment this thing. Just you take sand and you just keep it here and take one heavy ball, right? or heavy ball or heavy things also you can take. Now you drop it on a thick bed of the sand. Okay. So I have one ball, very heavy ball. Fine. Now I have to drop it. In this case, you can see that from 25 centimeter, I am just throwing this or dropping this ball. At that time, you can see that the ball creates some depression here, right? The ball creates some depression here. Now measure the depression height. Let it be h. Fine. Now do, in the same case, you do one thing. You just change the height of the object or height of the ball. You repeat this activity from 50 centimeter, 1 meter, 1.5 meter. And similar area, you please do not use the similar area. Suppose the ball you are falling from 1.5 meter here. So you can measure the depression. And after this, suppose, okay, just a minute. Okay, just a minute. Okay, from this, and you just measure the depression. So here from 1 meter, then from 50 centimeter, you just measure the depression, 50 centimeter in different places, right? Not in the same place. Now mark the depression to indicate the height from which the ball was dropped. So this is the depression. This is the depression due to 1.5 meter. This is the depression for 1 meter. And this much is the depression. This much is the depression for 50 centimeter, right? Now compare their depths. So first one from 1.5 meter. Second one from the same ball. Now you are throwing from 1 meter, then you are throwing it or dropping it from 50 centimeter, right? Now you measure which one of them is deepest and which one is shallowest and why it is. Just think about it. And what has caused the ball to make a deeper depth. So discuss and analyze among yourself. So you can see that whenever I'm just calling this from 1.5 meter, the depth is high. Okay, so because this displacement, that is 1.5 meter, that is highest. Okay, next activity, if we do this activity, these are the very interesting one. And one thing I have seen that to do all those activities, we do not require a lot of things, lot of costly things. Like you can collect the sand from here and there, and you can do it. Okay, so you can do it some construction area, maybe around your home or anywhere. So I don't think everyone can do it, but some of your friends, they can do it. Okay, so you can do it. Now another thing, another activity we'll do. Okay, let's move, let's start. So here, this is the setup. One table is here and one wooden block you have here, and having the known mass, the mass is known. And in front of the trolley at a convenient fixed distance, this is a trolley I have made, and place a known mass on the pan. So the trolley starts moving. So what happens? Here the trolley moves forward and hits the wooden block. Okay, this is the wooden block. This is the wooden block. Now fix a stop on the table in such a manner that the trolley stops after hitting the block. Then you can see that the block gets displaced. Note down the displacement of the block. So this means that the work is done on the block by the trolley because it has been displaced. That means what? If it has been displaced, that means yes, it has gained some energy. Without energy, how the work has been done? That means it has gained some energy. right? So this activity proves that yes, this has some energy. Now, from where does the energy comes? Here you can see that the mass is constant. So work done, it has done the work, and the work whatever done, that has been, due to that it possesses some energy. So that this setup you can make it in your home also. You can make it in your home also. So by definition, now again there will be some definition. By definition, the kinetic energy of a body moving with a certain velocity is equal to the work done on it to make it acquire that velocity. Okay. Now objects in motion possess energy and can do the work, right? And this energy is called the kinetic energy. So here the force F that equals to m into a, where m is the mass of object and a is the acceleration. Okay. Also, work done W that equals to your F into S, where F is the force, where F is the force and S is the displacement. Okay. Now, from the second equation of motion, we know that v square minus u square equals to twice as, right? That means s equals to v square minus u square whole divided by twice a. So let it be equation number 1. Let it be equation number 2. Now substituting equation of work done by a moving body, W equals to m into a into s. S is the v square minus u square whole divided by twice a. Let it be equation number 3. So taking initial velocity as 0, initial velocity u equals to 0, we will get that kinetic energy that equals to half of mv square. Equation number 4. So here the kinetic energy that equals to half mv square. This derivation is very, very important. Please take the screenshot as soon as possible so you can derive this one. So this derivation is very, very important. Fine. So kinetic energy, that is the half mv square, where k is the kinetic energy, m is the mass, already I have written, again I am writing, and v is the final velocity of the object, u is the initial velocity of the object. Okay, done. Next, when two identical bodies in motion, the body with a higher velocity has more kinetic energy. Okay, Whenever two bodies are in motion, at that time the kinetic energy will be higher, because the kinetic energy that is proportional to v square. So kinetic energy that is proportional to v square, because m is constant for any, m is constant we are thinking. So kinetic energy that is proportional to v square, as kinetic energy that equals to half mv square. That means if half into m that is constant, at that time kinetic energy is proportional to v square. So if more higher velocity, then kinetic energy will be higher. Okay, till now it's okay. Then thank you. Next lecture will start soon.